Hey, what is up? Asal here from InstaProofs. And for those of you who are currently in your first course of calculus, at some point or another you come across the following problems. X times natural log x, e to the x times the quantity sine x plus cosine x, the quantity 1 plus x squared times arctangent, and so on and so forth. And you're asked to find nothing but, well, the derivative. Sucks, I know, doesn't it? And you look through all the derivatives in your table of common derivatives in your calc textbook, be it the derivative of sine x, natural log x, or even x cubed complying to the power rule. But nothing seems to match up. And you skim through your basic derivative theorems, such as the derivative of a constant times a function being equal to that constant times the derivative of that function, or the derivative of the sum of two functions being equal to the sum of the derivatives of each of those functions, and so on, but still you come up empty. What do you do then? Well, there's nothing you really can do based on your current understanding, so you have to come up with a new rule. But before you can come up with that rule, you have to realize that all these functions have one thing in common, that they are the product of two or more separate functions. Take, for example, our first function, which is a product of two separate functions of x and natural log x, or our fourth function, which is a product of three separate functions, x cubed, e to the negative x, and sine squared. And similarly, the rest of the functions are such products. And the rule we devise to tackle the derivatives of these is called a product rule. And in this video, which will be part 1, we'll focus on just deriving that rule. So given a function f of x equal to k of x times g of x, a product of two separate functions, we want to derive the derivative of this function, or in other words, we want to derive the product rule. Keep in mind though that although the product rule only takes into account a function that is a product of two separate functions, it can still work on a function that is a product of infinitely multiple functions, as we can take the product rule on top of the product rule on top of the product rule as many times as necessary. The idea behind this you will see in part 2 of my examples video. So moving on. We write down our derivative, and the first thing we want to do is we want to apply the limit definition of the derivative, which is the derivative of f of x with respect to x equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. By the way, you should be very familiar with this limit definition of the derivative by now. And if you aren't, I doubt how you got this far in calculus, or your instructor is not taking their job seriously. So if you don't know this, do yourself a favor, write this down 10 times and memorize it, because this is a backbone of derivative calculus. So using this definition, and letting f of x equal k of x times g of x, and f of x plus h being k of x plus h times g of x plus h, and plugging in, we get the following. Now from here, if we left the limit as is, we wouldn't really get anywhere. Meaning, if you evaluate the limit right now, then we would get k of x times g of x minus k of x times g of x in the numerator, which is a 0, and we get 0 in the denominator, which is 0 over 0, or indeterminate. So the only option we have left to do is introduce new terms. And the new terms we introduce are minus k of x times g of x plus h, plus k of x times g of x plus h. And the exact logic behind why I'm introducing these terms, you will start to understand a little bit later throughout the derivation. Oh, and by the way, doing this is completely legal, because minus k of x times g of x plus h plus k of x times g of x plus h equals 0. So we're essentially adding 0 and not changing anything. So before any of you react or get any ideas and start adding terms when you're clearly not supposed to, I just want to get this across. So moving on and splitting the expression in the limit into 2 and applying the limit property that the limit of the sum of two functions is equal to the sum of the limit of each of those functions, we then get the following. And now the logic should be a little bit more apparent as to why I chose the terms that I did earlier, as we can conveniently factor out a g of x plus h from our first limit and k of x from our second limit, and further use the limit property that the limit of the product of two functions is equal to the product of the limit of each of those functions with our first limit and our second limit, and then arrive at this. Now, as of this point, it should be very obvious as to what our answer is going to look like. All that is left is to apply the finishing touches and evaluate the limits. So we proceed. So evaluating the first and third limit, we get g of x and k of x respectively for our rule so far. And then seeing that the limit k of x plus h minus k of x over h and g of x plus h minus g of x over h respectively are the following form, and seeing that this form equals the derivative of a function, we then get the derivative of k of x and the derivative of g of x plugged in as follows in our rule. And simplifying and rewriting in prime notation, we then have the quantity k of x times g of x prime equal to g of x times k prime of x plus k of x times g prime of x. And this here is our product rule. And for those of you who might have trouble memorizing this rule, just know that if you let k of x be the first function and g of x be the second function, and you let the derivative be denoted by a letter d, then the derivative is just d equal to first d second plus second d first, or vice versa, second d first plus first d second. I hope that quick mnemonic helps you out. So yeah, there you have the derivation. For examples, make sure to stay tuned for part 2, which will come out soon. Until next time, thanks for watching.